So alongside composite functions, we also want to think about something called inverse functions as well, which we've probably heard that word inverse functions being used for a long time really in maths, a really long time. So an inverse function, which we write f with this little 1, it does the opposite of, this little minus 1 to show that it's an inverse function. It does the opposite or the inverse of the original function. For example, if f of 4 gives you 2, then the inverse function of 2 gives you 4. Okay, so it does the inverse of that. And I've got this sort of diagram here to show that if you're going from the input to the output is f, then going backwards is f minus 1. It's nothing to do with like a reciprocal, it's just meaning the direction. This is going in one direction, this is going in the reverse direction here. So I've said just like f2 means apply f twice, f minus 1 means apply f minus 1 times. In other words, apply it once, but backwards. This is why we write the inverse sign as sign minus 1 to mean inverse sign. It doesn't actually mean the reciprocal like it does as a power. It means apply the function, but backwards. So this method that I have here, I never actually want you to use in questions, okay? Some people last year just thought this was the way to solve these problems. It is not. It's just a demonstration I used for an original example. So for example, if f of x is equal to 2x plus 1, we could do the opposite operations within the function in reverse order to get back to the original input. So f of x being 2x plus 1 means you take x, you multiply it by 2, and then you add 1. So to go backwards, you would take away 1 and divide by 2. In other words, you would take your value, you would take away 1, and you would divide it by 2 to get to what the inverse function was. But you should never use these flow diagrams to be able to do this, okay? You should do it with this next method I'll show you on the following slide here. So I've written, explain why the function must be a one-to-one function for an inverse function to exist. Why do you think that the function needs to be one-to-one for the inverse function to exist? Ishraq? Good. Good. If it were a many-to-one function, which is still a function, if you did the inverse, many-to-one would reverse to become one-to-many, which is not a function. So it's important that the function must be one-to-one, because if you do the inverse of one-to-one, it stays as one-to-one, and therefore both of them are functions. So what I've written here is if the mapping was many-to-one, then the inverse mapping would be one-to-many, but this is not a function. So if you could just add that in there. This has been asked in exams before, usually a little one-mark question. They'll say something like, does the inverse function exist? And you would have to decide whether the inverse function existed by thinking, is it many-to-one? And then it becomes one-to-many, which means it wouldn't exist. Okay? So this is going to be the proper way that we will find inverses of functions. In the original function, we have the output in terms of the input. We have a y equals function. And if we change the subject to get x in terms of y, then we would have the input in terms of the output, which is the inverse function. If you're trying to say what is the input when you know what the output is. So taking the original function and changing the subject to get x in terms of y, then you have the inverse function. However, we usually write functions always in terms of x. So what we need to do at the end is replace these so that the x and y swap places, and you actually end up with y equals x minus 1 over 2. So the inverse function is x minus 1 over 2. So you can either do it in this order. You can swap x and y, and then you can rearrange to make y the subject. That's slightly different to this order. This order, we made x the subject, and then we swapped x and y. I have found in the past that generally my students found it easier when they swap x and y to begin with, and then just rearrange it to make y the subject, and then say that that's the inverse function. It's exactly the same thing as this, apart from the swapping happens first. There's something about our brains that just really like to get y equals, because we've just done it for so long. So if you can make that happen quicker by switching them at the beginning, it works really nicely. So here, our original one is y equals 3 minus 4x. So what I'm going to do is I'm going to swap the x and y, and then I'm just going to rearrange it to make y the subject. So I would get x equals 3 minus 4y. So if I'm now making this thing, which is the input, if I'm making that the subject, it's going to do the inverse for me. So rearranging this, I get 4y equals 3 minus x. So y equals 3 minus x over 4. And you must finish that off by saying the inverse function is 3 minus x over 4. Swap them, rearrange to make the other one the subject. Okay, so we're going to do the same thing for this one. We have that f of x is equal to x plus 2 over 2x minus 1, and we're going to try and find the inverse. So to start with, it would normally be y equals x plus 2 over 2x minus 1. But we're going to swap the x's and y first, and then we're going to make y the subject. So we have x equals y plus 2 over 2y minus 1. So if I'm going to make y the subject, first of all I need to multiply up by the 2y minus 1. So I get x brackets 2y minus 1 equals y plus 2. Then I'm going to expand. So 2xy minus x equals y plus 2. Now if I'm trying to make y the subject here, what do I need to do to make y the subject? Because I've actually got two y's here. Y's onto one side and then factorize. So I'm going to put the y's on one of the sides. Now, depending on which side you put them on, you might get a different result. So in a second, I might show us both ways of doing it. So I'm going to put the y's onto the left-hand side. So I get 2xy minus y. Put this onto the other side equals x plus 2. And I'm just going to come up here now so I've got some space. I'll factorize, so I get y brackets 2x minus 1 equals x plus 2. So y is equal to x plus 2 over 2x minus 1, which means that the inverse function is x plus 2 over 2x minus 1. Do you notice anything? It's the same as the original function. So this is what we would describe as a self-inversing function. It's really weird, because if you put something into the function, if you wanted to find out what it was, you put it back into the same function again. Pardon? You did it the other way. Okay, so if you were to get them all onto the other side, what you would end up with is everything would have been negated. So you would have actually ended up with minus x minus 2 over 1 minus 2x. These two things here are actually the same as each other because they've been multiplied at the top and bottom by minus 1. That was because Ishraq put all of the y terms onto this side and all of the x terms onto this side. So they are the same thing here. So if you just think about it with a number, I don't know, let's put into this function, let's just put in f of 5. F of 5 would be 7 over 9. So if you wanted to find out what you put into the function, and you knew that what came out was 7 over 9, you actually put 7 over 9 back into the function. So I'm just going to do that on my calculator to save a bit of my brain this morning, but I don't know where I've put it. Here it is. It's self-inversing. So the same function actually undoes the thing that it did. So it's self-inversing. So if I put 7 over 9 back into this function, I would have 7 over 9 plus 2 divided by 2 times 7 over 9 minus 1, and you go back to 5. It's just a kind of a weird example of a function where if you put into the function the same thing, it just keeps going back and forth. Weird thing. This is a unique one. You're not going to get many of them that are self-inversing like that, okay? So yeah, if I put the inverse. Why can't it work? So why can't it equal a half? Yeah, good point. So why have they said for the domain here that x cannot be equal to a half? If it equaled a half, then the denominator would be 0, and that would not have an output. And remember, a function must have, every input must have an output. So they've told us that's not allowed to be an input in the domain there, okay? So the inverse function of 7 over 9 is actually the same as the function of 7 over 9, which from this information is just going to be 5. I just picked like a random number there. These are kind of strange the way they behave, so try and think carefully about what these mappings mean. You're also going to need to know how to do the graphs of inverse functions, okay? Now, graphing inverse functions, there's a really neat trick that allows you to do the graph of an inverse function. And what we did when we were finding inverse functions is effectively we swapped the x and y coordinates because we said that x and y were swapping places. So this swapping of the x and y actually means that the x-axis and the y-axis are swapped when you're trying to do a sketch of the inverse function. It kind of makes sense. If we're saying that everything that was x is now y, then the axes have swapped. And a swapping of the axes is actually a reflection in the line y equals x. So really what we should say here, I guess I should write this, here we go. I've got it written in this section down here. If you have your original function, y equals f of x, and your inverse function, y equals the inverse function x, they have the line y equals x as a line of symmetry, which means that if you have one and you want to find the other one, you can reflect them in the line y equals x. So we can reflect f of x in y equals x to graph its inverse. Kind of a weird idea, but the swapping of the x and y was the swapping of the x and y coordinates. And even if you just think of some random point, like the point 3, 10, if you swap x and y, it becomes 10, 3, which is a reflection in the line y equals x. So there's a couple of other things about this graph I just wanted to point out here. So the red graph is the function. The blue graph is the inverse function. And you can see here that the line y equals x is that line of symmetry, that this red one has been reflected over into the blue one. A couple of other things I wanted to point out is that the x-intercept of this graph has become the y-intercept of the other graph because of the swapping process that has happened. This vertical asymptote that we have here at x equals 1 has reflected or swapped so that it's a horizontal asymptote at y equals 1. So everything has swapped, but what that looks like is a flipping over the line y equals x. there are some other things that happened as well. The domain of this particular graph that I've got here, it only works for values of x that are greater than 1, and that's because of the asymptote that x is equal to 1. So the domain of f is that x is greater than 1. What that then corresponds to is that the range of the inverse function is the inverse function is greater than 1. What's the feature of the blue graph that shows me that the range is greater than 1? Yeah, it's the asymptote, and the range is the y-axis. So the range of this blue graph is the fact that it can achieve all of these values. The domain of the red graph is the fact that you can input all of these values. So basically, function and inverse functions are all about swapping. Domain becomes range, range becomes domain. And this application of things really becomes like a little way of like solving problems. It might be easier to find the range of the normal function in order to find the domain of the inverse function. So if a question's asking you to find one of those combos, it might be easier to find the flipped version of that, okay? And that's what I've written just down here. Same thing, that domain of the function is the same as the range of the inverse. But you would never write for the range of the inverse function. You wouldn't write that x is greater than 1. You obviously need to replace it and say that it's the inverse function. The range of that is greater than 1. Everything is swapped. Everything is switched, okay? Any questions on that before we try and apply it? Okay. So here we have got a function, g of x, and I just want to break down a little bit more about what it says here. It says that g of x is equal to the square root of x minus 2, and it says that x is a real number and x is greater than or equal to 2. So it's told us about the domain here, okay? This is the domain, and this is indeed a function, and this graph is going to look something. Do I have to sketch it? No, I'm going to sketch them later on in part C, so I won't do it just yet. The first thing that it wants us to do is to find the range of this graph that we've got here. Now, if we had the graph already, we could try and just say what values we could get. We're going to try and do it without a graph this time, seeing as it hasn't asked us to do any sketching just yet. So just think, if you're only allowed to put in numbers which are greater than or equal to 2, what kinds of answers could you get to this function if you were going to substitute in? Like, what's the smallest answer you could get? 0. The smallest answer you could get is 0, and that's when you put 2 into the function. If you put 2 into the function, the smallest thing that you could get here is 0. So that's telling me something, that the smallest thing that we can get is 0. I just want to investigate if there's like an upper ceiling on it. Do we think that there is a ceiling on what value we could get? No, because you could put in, it just says here that x is greater than 2. Whatever number you're thinking of, if you think of a bigger number, the range is going to get bigger as well. So the range for this particular function is just that it's got to be greater than or equal to 0, okay? Part B of the question is wanting us to do the inverse function. So we have, normally we say that it's gx equals the square root of x minus 2. I'm going to write it as y equals the square root of x minus 2. Don't forget this important step of switching the x and the y over, so that we get x equals the square root of y minus 2. And what should we do to both sides of the equation? Square it. So we get x squared equals y minus 2. So we get x squared plus 2 is equal to y. In other words, the inverse function is x squared plus 2. And it wants us to sketch the graphs of both functions. Now, you might not be sure about how you sketch these square root graphs. So if you wanted to, we could sketch this graph that we know how to do. And what could I do to then sketch the original graph? I could reflect it in the line y equals x. So I actually know what the square root graph looks like. I'm sure many of you do. But we're going to do that method just because I think it's interesting to think about. So I'm going to sketch x squared plus 2, so which is just going to be a nice, simple graph like this. Maybe it needs to be a bit more like this. I don't know if they're going to cross over. And then we're going to have a reflection of that in the line y equals x. Now this is where I don't know if it's going to cross over. We're just doing a sketch here. So I'm going to think about what my mirror line would look like this. And I'm going to reflect this. Now I'm only going to reflect this branch. You'll see why in just a second. And so when it reflects, you're going to get this kind of shape. Pardon? It would have been a one-to-many. Now, the fact that it doesn't say at the beginning plus and minus means that I don't have the negative branch. I'm only, because it just doesn't have that, it is obviously just talking about the positive root, which is why I've just got this section that I have here. And this bit was crossing at 2, so this bit here is crossing at 2. Again, this makes sense because a square root graph would normally start at 0 if it was the square root of x. But ours is the root of x minus 2. What transformation would this be to go from x to root x minus 2? It would be a translation of 2, 0. So it's actually moved from here to the right by 2 spaces. Okay? So we've sketched the graph of both functions. However, I think there's something that I need to remove. Which bit do you think I need to remove from the diagrams? The black bit needs to be removed because actually in the original function there is no negative branch because it just is the positive square root here. We always think of this as being plus and minus. If it doesn't say plus and minus, it just means plus, okay? So we're going to get rid of this black part that's here. And this is what the graphs of both functions look like. I'm not sure if they're crossing x. I would check that in a second. I don't know if they do, but you'd still get the mark because it's impossible really to know unless you do some solving of equations here. And then part D of the question wants us to state the domain and range of the inverse function of x. So I'm actually going to go to the original function. The domain was this, that x is greater than or equal to 2. And the range we worked out was that it was just greater than 0. Greater than or equal to 0. So when I'm going to look at the inverse function, what did we say happens with the domain and range? They swap. So the domain is going to become that x is greater than or equal to 0. That one has gone over here. And the range is going to be, let's match it the same way, is that the inverse function of x is greater than or equal to 2. And hopefully we can see both of these things on the graph. When we're talking about this inverse function, which I should have labeled really, when we're talking about the inverse function, clearly the input values have got to be greater than or equal to 0 because there's nothing over here on the left-hand side. And the range of values that you can get on the y-axis are 2 and above. Okay? I'm actually just going to put it on Desmos just to see if they should have crossed over because it's possible that they do cross over. So let's have a quick look on Desmos. No, it wouldn't affect the answers. It's just that my brain couldn't think about that, and you wouldn't get penalised for it either. So we have x squared plus 2, and then the square root of x minus 2. No, they don't cross over each other. I meant, do they cross the line y equals x like that? Okay, so that's what we'd sketched here. Okay, we're going to go a bit quicker because I've realised I'm being a bit slow in the way I'm describing these things, okay? Function is described as this. I tell you what, why don't you have a go at doing this one yourself, okay? Because I've been doing an awful lot of talking here. I'm going to just do it slowly on the board, but you guys can try it yourself. If you want to watch what I'm doing, you can watch what I'm doing, but I'm just going to do it myself, okay? Just a quick tip when you're doing the sketches, when you're sketching the original function, I hope you paid attention to this, that x is greater than 0. So you'll notice when I drew my function in black, I didn't have the negative branch because I was only allowing to put in positive values for x, and that was to make it a one-to-one function. Otherwise, it wouldn't have an inverse. Mostly done on A and B, everyone? Nearly? Okay, part C is, we're going to try and solve the equations, but I'm going to show you a shortcut in case, well, we'll see. Well, I'm just going to do it the normal way first. So we want to make this equal to this. So it's the square root of x plus 3 equals x squared minus 3 for solving the equation. What would I do to both sides? Square it. So if I square both sides, I get x plus 3 equals that whole thing squared. So that's x squared minus 3 squared, which becomes what? X to the power of 4 minus 6x squared plus 9, because you've got the negative 3 times the negative 3. So if you were going to make this equal 0, you would get x to the power of 4 minus 6x squared minus x plus 6. Now your calculators can do this, but in the old calculators they couldn't do this. So I'm going to show you a way you could have done it. So what's that? 1, 0, minus 6, minus 1, and 6. Now your calculator gives you a lot of different solutions. 4 different solutions. Now clearly by looking at the graph, there is only one solution where they all cross. So the ones that the calculator has given you are x equals 2.3 something, x equals 1, x equals minus 1.3 something, and x equals minus 2. Are there any of these that we can completely disregard? Because it's clearly crossing in the positive, so it's definitely not going to be either of these ones. How could I check to see if I think these ones work, which one it would be between them? I could substitute it in, so I'm going to test. I'm going to try out if x is equal to 1. So on the left-hand side, I would get the square root of x plus 3, which is the square root of 4, which is 2. The right-hand side is 1 squared minus 3, which is negative 2. So they actually don't cross. They're actually something else that's going on in the graph. So x equals 1 is also not a solution. So the solution is this one at the top, which is, now your calculator can't even get it in exact surd form. So I'm going to show you the way of getting it in exact surd form. If you notice what's happened here, this isn't actually just the crossing of 2 graphs. It's actually the crossing of 3 graphs. So instead of solving f of x being equal to f inverse of x, this is a really cheeky question. Instead of doing this up here, what you could have done is just solved, this is y equals x. You could have just solved y equals x being equal to either of those graphs. So I'm going to solve it being equal to the one in the question, x squared minus 3. So you get x squared minus x minus 3 is equal to 0. and then your calculator will actually be able to handle that. So you've got 1 minus 1 and minus 3. And so the solution is 1 plus the square root of 13 over 2. Because the negative 1 that you get from this is actually not on the graph. Kind of hard, kind of weird. Just thought I'd show that one as a bit of an extra thing.
So if we did 2.3 something, would that still be right?
It should be all right. If they'd said give your answer in exact form, your calculator couldn't handle it from this quartic. So you would have to have spotted that the solution where these two cross, they also cross at the line y equals x, which makes sense because that's the line of reflection. But the only reason I know that is because I taught this last year. When I looked at that question before, I did this and got stuck. Like, so it's not easy to spot this kind of stuff. It's just from my memory, I've spotted that before. Okay, we've only got about 5 minutes left. So I think what we'll do is we'll have a look at this example for the next lesson. It's also got some exponential stuff, which may be a bit tricky. I'm setting you some homework from exercise 2D, which is the even questions, I think I've said, for 2D. And the same for 2C as well. I don't see you for a whole week. I'll tell you about some of the other bits for homework as